Welcome to this presentation. My name is Pantic, Zeljko, and I'm an associate professor at North Carolina State University. The objective of this Power America project is to design, implement, and demonstrate an efficient operation of GaN-based Class C and Class EF2 inverters for a variable load impedance. We expect to achieve this goal by employing nonlinear, which means voltage-dependent capacitors, and by combining them with a GaN switch for an efficient operation. Class C type resonant inverters are intended for low and medium power applications, and they are typically operated in megahertz range. These single switch converters operate efficiently at high frequency due to a carefully selected network of reactive elements that surround, switch, and assure zero voltage switching and zero voltage derivative switching of the active device. That way, we eliminate the dominant terminal loss of the switch. The use of emerging GaN devices allows for further increase of frequency and efficiency. However, a Class C inverter has a significant deficiency as well. It operates as expected only for the specific load for which it has been designed. Therefore, for a while, since its invention in 1980s, these inverters were used for constant load applications. High-frequency operation of Class C inverters is very attractive for emerging wireless charging, since high frequency would allow for more spatial freedom and more distance between primary and secondary coils while still transferring the same power. However, a wireless charging application cannot guarantee a constant load. Let us look at the example of a wireless charger for an electric scooter. Really, there is no guarantee that the user will leave the scooter always at the same position, which causes coupling between primary and secondary coils to vary, and consequently it causes variable different load reflected back to the primary inverter. Moreover, component tolerance, component aging, and different objects in the environment can cause the detuning of the resonant tanks in the primary and secondary, which effectively reflects or appears as a variable reactance at the input of the primary inverter. As a conclusion, instead to have a single resistive load, as being designed for, Class C inverter must cope with a range of loads that has both resistive and reactive components. Let us illustrate this as on an example of a Class C inverter designed to deliver 200 watts while achieving efficiency of 95% for a rated load. Due to all these effects that I've just mentioned, the load impedance vary, which will cause the power and efficiency of this converter to vary too. On the right of this slide, you can see a Smith chart that illustrates the areas of the same efficiencies and the same powers. And this Smith chart shows that when the load varies in a specified range, the power varies all the way down to 50 watts and all of the way up over 300 watts, while the efficiency can be as low as 80%, 85%. To cope with the variable load problem, some researchers propose the use of active tuning of compensation circuits. The active tuning essentially negates one of the main advantages of resonant circuit, of resonant inverters: simplicity. Moreover, active tuning may not be fast enough in some cases to correct the tuning conditions before the switch is damaged. In this research, we propose to investigate if the development and the deployment of Development and deployment of a nonlinear voltage-dependent capacitor in the shunt circuit can alleviate the problem with the variable load. There are various types of nonlinear capacitor, and some of them are more suitable for application in question, and part of our research will be to determine the most suitable type of a capacitor and to design its values. Apart of the switch and inverter efficiency, there are two other parameters we are interested to track while optimizing the inverter. They are output power variation with respect to the rated power and switch utilization. Switch utilization is an effective measure of switch stress. In order to achieve the targets, we first need to learn how to analytically describe signal waveforms in a practical Class C inverter that uses a practical device that includes parasitic capacitance, reverse diode, resistance of the channel, etc. Then, after that, we are going to use those waveforms to accurately calculate the losses in the inverter. And finally, we are going to use waveforms and losses to optimize the system. So we need to derive an optimization algorithm and a smart optimization algorithm that will be capable of selecting the reactive components for a practical switch. An analytical procedure for calculating inverter signals is successfully derived for Class C and Class EF2 inverters. The waveform generated that way demonstrate an excellent resemblance with the SPICE results. This slide shows the waveforms for hard switching and soft switching conditions in Class C and Class EF2 inverters. It illustrates an excellent matching I was talking about. Moreover, it takes only a tiny fraction of time to calculate these waveforms compared to the time needed for SPICE simulator. Next step is to derive a model that accurately predicts losses in the inverter. That includes the GaN device switch losses. We consider both conductive and switching losses of the GaN device. For this application, for this modeling, as well as for the entire project, we decided to use GS66508B GaN device manufactured by GaN Systems. This is a 650-volt device. Also, we modeled the losses in reactive elements, including the parasitic equivalent series resistance related losses, as well as the losses related to magnetic fields. We ran the calculations of the efficiency calculations, and we got accurate loss model. This slide illustrates very good matching between the results we obtained analytically compared to the losses calculated from the SPICE model. Except for very hard switch conditions, the loss is calculated within an error less than 10%, which effectively results in an error less than 1% when we talk about efficiency. To perform multi-objective optimization, test points are defined. So we selected 17 test points that are uniformly distributed over the space of possible loads. Next, we specify 3 figures of merit that will be tracked during the optimization process. Those figures of merit actually match the variables I just talked about, efficiency, power, and switch utilization. We selected particle swarm optimization algorithm as the most suitable for this type of optimization to be our search engine. Finally, particle swarm optimization is developed and it is tested. It's capable of optimizing any weighted sum of 3 figures of merit that I've just defined. This project is continuing. Currently, we are finalizing nonlinear capacitor design. We are also finalizing the design of the charger, including the receiver coil and receiver power electronics. Prototype building will start in early August, and the experimental work is scheduled to begin in early October. Thank you very much for your attention.